Okay, then let's begin. So it's my pleasure to introduce Maxence Mayrand from University de Sherbrooke, and he's going to speak to us about reduction of Dirac realizations. Okay, take us away, Maxence.
Great, thank you. Thanks, Nikita, for the invitation. The goal of this talk is to introduce a paper that Ana Balibanu and I just posted on arXiv a few weeks back, called Reduction of Dirac Realizations. And it also builds on some previous work with Peter Crook's on symplectic reduction along a submanifold. So Peter already presented this paper at this seminar about a year ago, but I will recall a few key points for motivation. So, okay, let's begin by a brief overview of the main ideas of this talk. So suppose that you have a moment map for a Lie group action in the symplectic manifold, the usual moment map condition. And then we have the notion of symplectic reduction, the usual one. So for a point C in the dual of the Lie algebra, you can take the quotient of the inverse image of C under the moment map nu by the stabilizer subgroup G sub C. So that's a subgroup of the Lie group G. So that's a new symplectic manifold under good conditions. Now, with Peter, we introduce this notion of symplectic reduction along a submanifold, where the idea is to replace this level Xi by now a submanifold of the dual of the Lie algebra, satisfying some non-degeneracy conditions, where the main idea with the distinction with symplectic reduction is that now the thing by which we take the quotient is no longer a subgroup of G, but now a subgroupoid of the cotangent bundle, the cotangent groupoid associated with G. So that's a new symplectic manifold under good conditions. And of course, now you can generalize replacing the cotangent groupoid by any symplectic groupoid. And then X here plays the role of the dual of the Lie algebra, and for a submanifold S inside X, which is that to degenerate, so a pre-Poisson submanifold is the right condition, then you get a notion of quotient. So one of the main examples, which was the motivation for this, is to explain a construction of Ginzburg and Kazhdan, which is a kind of symplectic reduction by a universal centralizer. So that's a particular example of a groupoid. It's a group scheme, so that's a groupoid where the source and target maps are equal. And so they had this construction as a solution to the so-called Moore-Tachikawa conjecture, which was something I will recall in the next few slides. It's a very interesting conjecture which motivates this work. So that was the case of symplectic groupoids. And then with Ana, we developed a generalization for Dirac realizations. First of all, there's a global version, which is a direct generalization of that, where we replace symplectic groupoids by quasi-symplectic groupoids. So that means the integration of a Dirac manifold. So just like Poisson manifolds integrate to symplectic groupoids, Dirac manifolds integrate to quasi-symplectic groupoids, or sometimes called twisted pre-symplectic groupoids. So now a reduction level, generalizing C, a point in the dual of the Lie algebra, slightly more complicated. It's a submanifold with a 2 form, with some compatibility conditions with the 3 form on X and other things. And then from this data, there's a canonical subgroupoid G sub S gamma of the quasi-symplectic groupoid G, such that this quotient is now a new Dirac manifold. And so this is something that we can derive from shifted symplectic geometry. That's one way to motivate this construction. I will explain how to do that. And then once we have this version, then we can, we can first of all prove it just like with normal differential geometry, but also we can imagine a more general infinitesimal version for a Dirac realization. So that means Dirac realization, you can think of them as Dirac valued moment maps. So it generalizes Lie group valued moment maps and standard moment maps valued in the dual of the Lie algebra. So in this case, we lose the interpretation in shifted symplectic geometry, but it's more general. So we have S, a submanifold of X with a 2 form, and a map to a Dirac manifold, and under various compatibility conditions and non-degeneracy assumptions, we get a new Dirac realization. So a Z-valued moment map for Z Dirac manifold as a quotient of this Dirac realization. And so one of the applications is to get multiplicative versions of some moment map constructions. And one of them is a multiplicative version of the Moore-Tachikawa TQFT and other things like a notion of symplectic reduction, quasi-Hamiltonian reduction by the subgroups and things like that. Okay, so let's begin with the main motivation for that construction, which is the Moore and Tachikawa conjecture. Okay, so the idea is that we have a complex semi-simple group fixed throughout, and then we have two natural Hamiltonian manifolds associated to that group. First, the cotangent bundle of the group itself has Hamiltonian actions of G cross G by left and right translation, left and right multiplications on G lifts to a Hamiltonian action on this cotangent manifold, which is here is the canonical symplectic form of a cotangent bundle. And another nice one is you take the so-called constant slice of the group. So that's a slice for the coadjoint action of G on the set of regular elements. So that's a symplectic manifold. And the left action, the action of G on this left factor here by left multiplication is Hamiltonian, giving you a Hamiltonian G manifold. Okay,
so just to make sure, on the picture, it looks like S in chosen in the second copy, but you're saying the left action survives. So G acts, even though you write it on the right, it acts on the left. Is it right?
It acts on the left, yeah, sorry.
Okay, no, it's okay, just to make sure.
Yeah. Yeah, I put it on the right for this picture here, but it's not, yeah, it acts on the left. So yeah, we have these two Hamiltonian manifolds here, and I will think of them as being formally associated with the cap and the cylinder respectively. And I'm not saying it's a moduli space of objects on these surfaces, I'm just like labeling them with these Hamiltonian spaces. And the goal of this conjecture is to extend this list to associate to each closed oriented surface with boundaries a Hamiltonian space, which has many commuting G actions as there are boundary components of the surface. So here we have 3 boundary components, 3 G actions. And they must satisfy certain compatibility conditions, namely, if you have 2 surfaces, then you get 2 Hamiltonian spaces associated with them. So here's one, here's a second, but you can also glue the surface together and output another Hamiltonian G space, the one on the right-hand side. But if you look at these 2 Hamiltonian G spaces and take this boundary component where we do the gluing, this one has 3 G actions coming from these 3 boundary components. So we can single out one of these G actions, and same for this one, and do the symplectic reduction along the diagonal action of G on these 2 Hamiltonian manifolds. So that's a new Hamiltonian here, in this case, G cross G space. And it should be isomorphic to the one on the right-hand side. So the conjecture is that such an association from closed surfaces to Hamiltonian spaces exists. And you can think of it more precisely as some kind of topological quantum field theory, which just means a symmetric Mondrian functor from a category of cobordisms, 2-dimensional cobordisms, to a central category of Hamiltonian spaces, where this category is objects or Lie groups, and morphisms or Hamiltonian spaces, where the composition is given by this identity. So if you're familiar with that, you can think of this as embedded in the category of Morita equivalences of symplectic groupoids. But the distinction is that here everything are complex affine varieties, and whenever we take a quotient, we have to do it in the sense of geometric invariant theory, so taking spectrum of invariant polynomials, so that we stay with affine varieties. But it's the same idea. Okay, so why is this an interesting and highly non-trivial conjecture? It's mainly because of its examples. First of all, it suffices to construct the variety associated with the 3-punctured sphere, the pair of pens, because any surface can be decomposed into 2 pieces consisting of these pair of pens or the cap, and the cap is part of the conjecture if I go back cap we associated with it. And this is associated to the cylinder to the cotangent bundle because it's kind of the identity in this category. So it suffices to construct this variety. So that's supposed to be a Hamiltonian G cross G cross G space. So through 3 commuting Hamiltonian actions of G. And in the case of SL2C, it turns out to be the standard representation of SL2C tensored with itself 3 times. And now, surprisingly, in the case of SL3C, it's the closure of the minimal important orbit in E6. And then after that, they didn't know the answer. That was the original, in the original paper of Moore-Tachikawa, they had these examples. It's hard to see the pattern here, like what goes next and why does E6 pops out of SL3C. So that's interesting. But Ginzburg and Kazhdan came along and they found a uniform way of constructing these varieties as follows. So it's a special case of co-isotropic reduction, but it has more structure, as I will explain. So suppose that you have a symplectic manifold. So let me just briefly recap what is co-isotropic reduction, and then I will explain their construction. So a co-isotropic submanifold means that the symplectic orthogonal of the tangent space is contained in the tangent space of that manifold. And the fact that omega is a closed 2 form implies that this is an integral distribution. So you can take the leaf space. And if this leaf space is a smooth manifold, then omega descends to a symplectic form of that because we're quotienting by the space in which the symplectic form degenerates. So the structure, the symplectic or the 2 form on the quotient is non-degenerate, it's a closed non-degenerate form. So the main example that everyone knows is if you have a moment map for a Lie group action, you take the pre-image of 0 under the moment map. And somehow the miracle of symplectic reduction is that in this specific case, the leaves of this distribution are precisely the G orbits for the action of the group G you started with, which explains why the quotient by G of the 0 level set of the moment map is a symplectic manifold if it's smooth. Okay, so the Ginzburg and Kazhdan construction is an example of that co-isotropic reduction, but here the leaves will be groupoid orbits instead of group orbits. So the idea is to build the variety associated with the n-punctured sphere uniformly. So that's supposed to be a Hamiltonian Gn space, and we build it by gluing in some way the variety associated with the cap. So that's Z1. By definition of the conjecture, so this Z1 is G cross S, where S is the constant slice. So that's a symplectic manifold. And it's a Hamiltonian G space. It has a fibration to S by just projecting into the X vector. And the key lemma is that if you do the n-fold fiber product of this, called this N, of this fibration, this is co-isotropic in the n-fold product of Z1. So that's a symplectic manifold. And moreover, the leaves of the null foliation in this case are not orbits of a group, but a certain groupoid H, which is more precisely defined using the universal centralizer of G. So that's a groupoid whose source and target maps are equal. So it's a group scheme whose fibers, it's a group scheme over S, whose fibers are centralizers of these limits. So then if you take the quotient by this groupoid action, you get something symplectic. It's not quite the answer because, as I said, we have to take GIT quotient. So here this quotient should be in the sense of geometric invariant theory, meaning a spectrum of invariant polynomials. And then there's the issue of showing that you get an actual variety in just an abstract scheme. So that means that you have to show that these polynomial rings are finitely generated, which is true in type A, but so far, as far as I know, I don't think it has been proved for other types. So this still mystery.
Makes sense. Just to better understand this curly H, the groupoid, you say it's a kernel of z times z times z to z over c. What is c?
Oh, sorry. C is S. Sure. In previous version, I
it's
had
S.
the
Okay,
other
okay.
thing, but yeah, C should be S. Yeah.
Okay, thank you.
So here it's an abelian group scheme. So that's the multiplication map. So since Z is abelian, the multiplication map is a groupoid morphism, and the kernel is then therefore a subgroupoid. Thanks for pointing that out. Okay, so yeah, so since we have something which is it's a quasi-tropic reduction, but it has more structure, which is very reminiscent of the example of a moment map where we have g orbits are the leaves of the foliation. Now it's h orbit for some groupoid. So the question is, can we see this n as some kind of moment map condition for a more general theory of symplectic reduction by a groupoid, which includes this example? So that was the input, the motivation for this this work.
May I ask one more question?
Yeah.
So this Ginzburg-Kazhdan construction, maybe I already asked you at some point, does it have some interpretation in terms of moduli or flat connections? Of course, we would imagine that there should be natural gluing for moduli or flat connections. Can you decorate, modify in some way moduli or flat connections so as to get this gadget?
No, well, I don't. Maybe it's possible, but no one has found how to do this as a moduli space yet. It's yeah, it would be very interesting to have some more moduli space interpretation of that. But as far as I know, this is not. There's no interpretation as such yet. But it would be nice to find one.
Oh, okay, thank you.
So. With Peter, we define this notion of symplectic reduction along a submanifold as a motivation, as a way to answer this question. And then with Ana, we developed a Dirac version, which in particular, if you take a Lie group with its Cartan Dirac structure and you do the same kind of reduction of construction, you get a multiplicative version of this TQFT where we get quasi-Hamiltonian G spaces, and then the composition is obtained with a fusion product and quasi-Hamiltonian reduction. So I will explain that in a moment. Okay, so let's talk about, just briefly recap twisted Dirac structures before introducing our construction. So if you have X, a smooth manifold with Fourier closed free form, then there's this notion of phi twisted Dirac structure, which means a subbundle of the tangent bundle plus its cotangent bundle, which is Lagrangian with respect to this canonical symmetric pairing, and involutive with respect to this Courant bracket twisted by phi. So it generalizes many things, like symplectic manifolds are a Dirac structure if you take the graph of the two form. The involutivity is equivalent to the closedness of the two form. Marginally quasi-Hamiltonian manifold are also obtained of this form, and marginally Poisson and quasi-Poisson manifolds are examples of twisted Dirac structures. Okay, and there's a moment map theory for Dirac structures. First of all, I will discuss the global version because it's suitable for our interpretation in shifted symplectic geometry. So a phi twisted Dirac manifold has a notion of integration to a groupoid, just like symplectic, just like Poisson manifolds integrate to symplectic groupoids. And so that's why they are called sometimes quasi-symplectic groupoids. That's the terminology introduced by Ping-Xu, or twisted presymplectic groupoids by Bernstein, Koenig, Weinstein, and Zhu. So, and there's also a notion of a Hamiltonian G space. So that's an action of a quasi-symplectic groupoid on a manifold endowed with a through form with various compatibility conditions. So this generalizes standard Hamiltonian G spaces for a Lie group G, where we take X to be the dual of the Lie algebra, and quasi-Hamiltonian G spaces where if we take X to be a Lie group G whose Lie algebra has a non-degenerate symmetric pairing, there's a Dirac structure on that called the quotient Dirac structure. Okay, and there's also a reduction procedure introduced by Ping-Xu. If you take X a point in the base X, which plays the role of the dual of the Lie algebra, then the preimage of X under the moment map, quotiented by the isotropy group at X, is now a new symplectic manifold, at least if it's a smooth manifold. So that's the reduction procedure. So it looks like a theory of symplectic theory of reduction by groupoids, but the issue is that in the end we're still quotienting by a group, an ordinary group G sub X. So this cannot in any way recover the construction of Ginsburg and Kazan, since the quotient at the end was by a groupoid. So we have to generalize that. And the idea is to replace this X here, the singleton in X, by a submanifold, which will produce a canonical subgroupoid over that submanifold S, so that the quotient is a symplectic homogeneous Dirac. So that's the notion of Dirac reduction along a submanifold. And one way to introduce it is using shifted symplectic geometry. So in shifted symplectic geometry, one of the main constructions is if you have an n-shifted symplectic stack and two Lagrangians, so that's morphisms of stacks with additional structures, making it generalizing the notion of Lagrangian manifold in normal symplectic geometry. Then the fiber product of these two Lagrangians is n-1 shifted symplectic. So in particular, if you have something which is one shifted symplectic and you find two Lagrangians, you get zero shifted symplectic, which means ordinary symplectic geometry. So that's the idea. Okay, so rather than giving an introduction to shifted symplectic geometry, I will just build a dictionary between differential geometric concepts and concepts in shifted symplectic geometry. So first of all, a quasi-symplectic groupoid, meaning an integration of a twisted Dirac structure, gives an example of a one-shifted symplectic stack. And in fact, if you give a quotient stack of this form, the structure of a one-shifted symplectic structure, this is equivalent to giving this groupoid the structure of a quasi-symplectic groupoid. So there's a one-to-one correspondence here between one-shifted symplectic structures on quotient stacks and quasi-symplectic groupoids. Next, we have, suppose we have a Hamiltonian G space in the sense of Ping-Xu. Then there's a map from the quotient stack of M by G to the quotient stack of X by G induced by the moment map. And there turns out to be a Lagrangian in the sense of shifted symplectic geometry. And this is also some, in a sense, an equivalence if you have an action of G on M. Then there's this maps of quotient stacks, and giving a Lagrangian structure on it is equivalent to giving this M the structure of Hamiltonian G space. Okay, so we have one shifted symplectic thing and one Lagrangian. So any second Lagrangian will give something zero shifted symplectic, which is ordinary symplectic geometry. So one place to look for is the subgroupoid. So if you take a subgroupoid of a quasi-symplectic groupoid, this will induce a map of quotient stacks. And then you may ask what kind of structure do we need so that this map is Lagrangian. And so in purely differential geometric term, it can be characterized as follows. So what we need is a two form on S, such that the pullback of the three form on X is minus d gamma. So gamma is a primitive for this three form phi pullback to S. And what's interesting is that the Lie algebroid of H is canonically determined by this data, this S and gamma. So it's a subgroupoid, meaning that the Lie algebroid of H is a subalgebroid of the Lie algebroid of G, which is just the Dirac structure Lx. The Lie algebroid G integrates this Dirac structure Lx, which is a Lie algebroid. And this Lie algebroid is completely determined by S and gamma. It's the set of pairs V alpha in the Dirac structure, such that V is tangent to S. And then V, you can take the interior product with gamma to get a one form on S, but also alpha, if you pull it back to S along this map, you get another one form, and these two have to be equal. So that's a canonical subset of the Dirac structure induced by this choice of S and gamma. And in fact, if you assume it has constant rank, it is always a Lie algebraid, so you can integrate it to a groupoid. And the third condition is a more global condition where you require compatibility between the two form of the quasi-symplectic groupoid and this two form gamma. So, so now you can forget about shifted symplectic geometry and define a reduction level of a twisted Dirac manifold X to be a submanifold S with a two form, which is a primitive for the pullback of phi, and such that this particular subset of the Dirac structure has constant rank. And the stabilizer subgroupoid of this reduction level is an integration of this Lie algebraid with this additional global property. And then a corollary of this theorem of Pentev, Toinbaki, and Vesossi is that if you take, you can define this quotient of the preimage of S under mu by this stabilizer subgroupoid, because now we can interpret this quotient as an intersection of two Lagrangians in this one shifted symplectic stack. So this is zero shifted symplectic. So in particular, if it's smooth, it's just an ordinary symplectic manifold. And if it's not smooth, well, we can at least say that it's a zero shifted symplectic stack. Okay, so this correspondence between Lagrangians, substack, and groupoids with these properties is a proposition in our paper with Ana. And then we use this, we can use this theorem to infer that, but you can also forget about shifted symplectic geometry. Once you know what to prove, you can just prove it directly with normal differential geometry. Okay, let's, before generalizing to the infinitesimal version, let's talk about some examples. So if you take an ordinary moment map for Hamiltonian G space and S is a manifold, then this Lie algebraid is a nice explicit form. So take the Poisson map from the cotangent bundle to the tangent bundle, and then take the preimage of the tangent space, intersect that with the annihilator. That's a subset of the cotangent bundle, which is the Lie algebraid. This has to have constant rank. So this kind of non-degeneracy condition, which in the literature is also known as being pre-Poisson. And then in that case, you have a canonical groupoid sitting inside T star G, which is the integration of that, such that taking the quotient by this groupoid of the preimage of S is symplectic. So we define this to be the symplectic reduction of M by G at level S, where S now is a submanifold of the dual of the Lie algebra rather than a point. So of course, if you do this with a singleton, you recover the usual Marsden and Weinstein reduction. Another nice example, if you do it with a Poisson transversal, you get that this groupoid here is trivial, and hence the preimage, you recover the fact that the preimage of a Poisson transversal under a moment map is a symplectic submanifold. And so that's kind of the other extreme. And another thing you can do is just take a Lie group and a submanifold of the dual of the Lie algebra, and this outputs a Hamiltonian G space, where you take the cotangent bundle of G. This is a Hamiltonian G cross G space, and if you do reduction on one of the two G actions along at level S, then this gives you a Hamiltonian G space. And it's a nice universal space for Hamiltonian reduction, in the sense that any Hamiltonian reduction along this S can be factored through usual symplectic reduction at level 0 of a product of M with this universal space. So it's kind of a nice construction where you can just take...
Maxence?
Yes.
Just a question, this M minus, does it mean something, or?
Yeah, opposite symplectic form.
Oh, thank you.
Yeah. It's like in the shifting trick.
And the S in this construction can be any submanifold whatsoever?
Pre-Poisson. Oh, you mean here? Yes, pre-Poisson submanifold. And you need the quotient to be smooth, so some non-degeneracy condition also. But yeah.
S has to be pre-Poisson?
Yes.
Okay.
which just means that this bundle here has constant rank. So so you can play with examples, and for instance, what we can take is a closed Weil chamber in a compact Lie group. It's not quite a submanifold, but it's kind of a stratified space of whose strata are pure Poisson submanifolds. And this recovers the universal implosion of Curie-Jeffrey-Shamma as a consequence. And of course, we recover the Ginzburg and Kazhdan varieties. This was the main motivation. If you take a complex semi-simple group and as a constant slice, then if you take the diagonal of this slice, so here S is as I recall earlier, it's a slice for the coadjoint action of the set of regular elements. Now our reduction level will be the diagonal in the n-fold product of the dual of the Lie algebra. And this universal space here will be a Hamiltonian GN space, and it recovers directly the construction of Ginsburg and Kazan, which is the space associated with the in-sphere punctures. So here, this stabilizer subgroupoid is this kernel of the n-fold multiplication map. And so that's the moment map condition is obtained by this preimage of the diagonal, and then this is the stabilizer subgroupoid. Okay, so let's go back to the previous slide. So that's our construction in the global version, but as I said, we can forget about shifted symplectic geometry and just prove this directly, but also there's a more general version. Once we know what to prove, we can try to generalize that. We lose the interpretation in shifted symplectic geometry, but we get something which is more general. So let's do that. It has to do with Dirac realizations. So a Dirac realization, you can think of this as a Dirac valued moment map, generalizing Lie group valued moment maps and ordinary valued moment maps, where the target is a Dirac, twisted Dirac manifold. So a Dirac realization, or sometimes called a strong Dirac map, is a map between twisted Dirac manifolds, such that it's a forward Dirac map. There's a notion of the push forward of a Dirac structure. The push forward of Dirac structure on M should be the Dirac structure on X. Compatibility with the three forms. And this is the non-degeneracy condition that the kernel of this, the differential of this map should intersect the Dirac structure trivially. So main examples, if you think of Dirac realization of the dual of a Lie algebra, you recover Hamiltonian Poisson G manifolds, or in other words, Poisson map to the dual of the Lie algebra, and also Dirac realization of a Lie group G endowed with this Cartan Dirac structure induced by non-degenerate symmetric binomial form. This recovers Hamiltonian quasi-Poisson G manifolds. So those like quasi-Poisson manifolds where the action is only local. So that's a result of Bernstein and Crank. And also, if you have a quasi-symplectic groupoid in a Hamiltonian G space in the sense of pink shoe that we had before, the moment map is automatically a Dirac realization. Conversely, you can integrate that a pre-symplectic Dirac realization to a local Hamiltonian G space with a local action of the quasi-symplectic groupoid. Okay, so now our notion of reduction of Dirac realization is as follows. So that's the infinitesimal version of the construction. So first of all, we can generalize the notion of reduction levels. So we have a phi-twisted Dirac manifold X, and a reduction level is submanifold, as we had before, a two form, and also a map to another Dirac manifold we will call Z, could be twisted also. And then certain compatibility conditions has to be satisfied. So the Lie algebroid we had before can be modified with this map F. So it's the set of pairs V alpha, where V is tangent to S, but also in the kernel of the differential of this map. And the same condition we had before. So the interproduct of V with gamma is a one form on S. And so is the pullback of alpha to S. So we can require that they are equal. And we require that this bundle has constant rank. And in this case, we call it the stabilizer subalgebraid of this set of data, because it turns out to be a Lie algebraid if it has constant rank. And this map has to be some kind of forward Dirac map, in the sense that if you take the pullback of the Dirac structure on X to S, and then do the gauge transform with this two form gamma, or minus gamma, then the push forward of that should be LZ, Dirac structure on Z. And then previously we had a condition where the pullback of phi had to be exact, given by minus d gamma. We can relax that. In most cases, it's what we have is this condition that the pullback of phi is exact and is minus d gamma. But more generally, we can require it to be exact only along the leaves of this, the action of this Lie algebraid, meaning the projection onto TS is the anchor map for this Lie algebraid, and that this has to sit in the kernel of these this three form. Okay, so now suppose that's the reduction data, and suppose now you have a Dirac realization which intersects this submanifold S cleanly. Then the main theorem is that this stabilizer subalgebraid is actually a Lie algebraid, and it acts on this preimage of S, such that the quotient, if it's a manifold, has the structure of a Dirac realization to Z, this manifold Z. Also, it has a nice, the nice fact is that the condition that this algebraid acts freely is the same as the condition that S intersects mu transversely, which is kind of a generalization of the familiar fact for standard moment maps that 0 is a regular value of a moment map, if only if the action is locally free on the level set. Also, if phi is 0, we have a non-twisted structures, for example, an ordinary Poisson manifold, then we can always take gamma to be 0 and Z to be a point. And in this case, there remains only a non-degeneracy condition 1. So it's quite flexible. It's just that this bundle the rank doesn't jump along the submanifold. And in this case, then the quotient is Poisson, because a Dirac realization over a point is the same thing as a Poisson manifold. Also, if we take S to be a singleton, then we get the notion of reduction of Dirac realization, which was already appeared in the original paper of Bernstein and Kreinig. So what we do is kind of a generalization of that, where we reduce along a submanifold instead of a point. Okay, so let's discuss now the special case where this X here, this twisted Dirac manifold, is a Lie group G endowed with a Cartan Dirac structure. So this gives a nice construction. Suppose you have a quasi-Poisson G cross K space here, in the sense of Alexeev, Kazhdan, Schwarzbach, and Mayrand. It can also be a quasi-Hamiltonian space, and the result will be quasi-Hamiltonian in this case. So non-degenerate quotient of something non-degenerate will also be non-degenerate. So in this case, what we need, well, the term is more general than that, but that's a special case, which is useful in practice. If you need a submanifold of G such that the pullback of the Cartan 3 form is exact for some gamma, and that this subalgebraid AS gamma has constant rank, the same that we had in the previous slide. I will not describe it explicitly, but it's some kind of canonical bundle that has to have constant rank. So this is a non-degeneracy condition. Then in this case, there's a canonical groupoid sitting inside the double instead of the cotangent bundle, such that the quotient of the preimage of S by mu by this groupoid is a quasi-Poisson K manifold if it's smooth. So that's what we define to be the quasi-Hamiltonian reduction of M by G at level S gamma. So if you take a conjugacy class, for example, and gamma will be the quasi-Hamiltonian form of this conjugacy class, then you get the quotient of the preimage of the orbit by G, and this recovers the usual quasi-Poisson or quasi-Hamiltonian if you start with something quasi-Hamiltonian. Reduction along conjugacy class. This recovers, as expected, the standard notion. Another nice example is taking a Sternberg slice. So if G is a simply connected complex semi-simple group, a Sternberg slice is kind of the multiplicative version of the constant slice that we had before. So it's a slice for the conjugation action of G on the set of regular elements. So explicitly it has this form, but it's not too important. So this is a coxeter element for the Weil group, and U is a maximal unipotent subgroup. And you take this intersection. Here is the opposite maximal unipotent subgroup. Well, there's a choice of Borel here also. Anyway. So in this case, the Cartan 3 form is 0, so you can just take gamma to be 0. And we get that this subgroupoid here is trivial. And so as a corollary, this notion of quasi-Poisson reduction is just the preimage of the Sternberg slice. And so we get that this is a quasi-Poisson K-manifold. So this is a result of Ana that she presented at this conference also a bit more than a year ago. And it actually motivated this collaboration. So when I saw Ana's talk at this conference, we started talking about possible ways to do symplectic quasi-Hamiltonian reduction along the submanifold, and then realized this could be done in the more general Dirac setting later on. So another example is the multiplicative Moore-Tachikawa TQFT. So if you take S to be the diagonal of this Sternberg slice in Gn, then so we do exactly the same thing as we had for the additive Moore-Tachikawa TQFT, but now we replace the constant slice by the Sternberg slice and the cotangent bundle by the double. So this is the double of Gn. Then this gives us a quasi-Hamiltonian Gn manifold. And then we associate this with the n-punctured sphere. And then we checked that this can be extended to a map associating closed-oriented surfaces with quasi-Hamiltonian G spaces, such that it has as many G actions as there are boundary components. And then it satisfies this compatibility condition where if you have two surfaces and then you do the gluing along one of the boundary components, this is a quasi-Hamiltonian G space. G, in this case, this specific case, this is G cross G space. But also you can do the fusion product of these two quasi-Hamiltonian spaces and reduce at level 1. Gives you a new quasi-Hamiltonian space, and these have to be isomorphic. So we get some kind of TQFT valued in quasi-Hamiltonian spaces. But the only thing remaining is to get an actual TQFT, we have to take the GIT quotients. And so this requires showing that certain ring of invariant polynomial functions on these affine varieties are finitely generated. And an interesting question for the future. So if we do all this setup, but with the GIT quotients instead of regular quotients, we should get an actual topological quantum field theory. What we have described here is some kind of open sets of these GIT quotients. Another question also, that is the definition of that would be the definition of our notion of quasi-Hamiltonian reduction along some manifold, where we take spectrum of invariant polynomials where M here is assumed to be an affine variety, and so is S. It would be also interesting to have an analog. So in the additive case, we had that the variety associated with the three-punctured sphere was the minimal nilpotent orbit in the Lie algebra E6. So one may ask if well, the corresponding multiplicative version holds is under this construction, do we get the minimal unipotent conjugacy class in the Lie group E6, exceptional Lie group E6? That would be very, very interesting. Okay, another example, if you take compact simply connected T maximal torus and an alcove, a dominant alcove, so that's a fundamental domain for the affine Wald group. This is the example for SU3. We're taking the alcove whose closure containing 0 here in a given Wald chamber. Then our S will be the image of the exponential map, the image of the closure of this under the exponential map. That's a submanifold of G. And it has a map to the torus. And then we can take gamma to be 0. And this gives a reduction level. So S is a submanifold with a 2 form in a map to another Dirac manifold. And so given a quasi-Hamiltonian G space, if you reduce at this reduction level, you get a quasi-Hamiltonian T space canonically from that. It's not quite a manifold because this S here is a stratified space, so you get a kind of stratified quasi-Hamiltonian T space. And this recovers the group-valued implosion of Urtubis, Jeffrey, and Chama. So that's a quasi-Hamiltonian T space whose quasi-Hamiltonian reduction is the same as the quasi-Hamiltonian reduction of the original space by G. So it's an abilization construction for quasi-Hamiltonian spaces. Another thing we get is a notion of quasi-Poisson reduction by a subgroup. So if you have a quasi-Poisson G cross K manifold, H a subgroup, then in general, it is not the case that we get a quasi-Poisson H cross K manifold. So unlike the additive case, where if you have a Hamiltonian G space and a subgroup of G, you always get a Hamiltonian H space, but not necessarily for quasi-Poisson manifold, because for one thing, there's no map from G to H, no canonical map from G to H in general. But we can have a notion of quasi-Poisson reduction if we suppose that the perpendicular of the Lie algebra of H is also a Lie subalgebra, and we let H per be its integration. So for example, if H is a parabolic subgroup in a complex reductive group, this is an example. The uniproton radical of this parabolic is also an example, or its commutator subgroup. So this gives many examples in the geometric representation theory. Then the proposition is that we can get a reduction level in our sense with this subgroup. You take the H perp, this will be a reduction level, and then you map that into the quotient of H perp by the intersection with H. So this is always a Lie group because this intersection is a normal subgroup of H perp. So you get so you get a reduction level, and the stabilizer subalgebrate is the actual Lie algebrate of H on H perp. So as a corollary, we get that the quotient, the preimage of H perp on the mu quotiented by H is a quasi-Poisson H perp over H cap H perp cross K manifold is smooth. And so this can also be recovered by a result of Severa and Librand, although we didn't know when we posted the paper on arXiv, so we learned that afterwards, and we'll make modifications of the paper very soon. But in this paper of Severa and Librand, where they discuss morphisms of Manin pairs, they have a result which implies this one as well. And so if we take the quotient further by this factor, we get that the inverse image of H perp by this product group is quasi-Poisson K manifold, and then we can describe the quasi-Hamiltonian leaves also. This is for each conjugacy class in this group here. The preimage under the quotient map here gives us a subset of H perp, and then we take the quotient by H perp. So for example, let's say a concrete example which recovers spaces defined by Philip Bolch on his study of moduli space of meromorphic connections. So if you have a parabolic group P of a complex reductive group G and a unipotent radical, and a Levy factor, L, then if you do the quasi-Hamiltonian reduction in this sense along U, this gives us this. So this is G cross P quotiented by the action of U, where U acts on G by right multiplications and on P by conjugation. And this will be a quasi-Hamiltonian L space, this quotient group here. It turns out to be just L, the Levy factor. And so if you do the further quotient, you get a quasi-Poisson G manifold structure on this space, which is also known as the multiplicative quotient Springer resolution. And the quasi-Hamiltonian leaves are given by these spaces where O is a conjugacy class of the Levy factor, which is a reductive group. So yeah, so this recovers nice spaces from nice examples of quasi-Hamiltonian spaces in Lie theory. Okay, so let me just finish by putting back the main theorem, and then I will end here. Thank you.
Thanks a lot.
Thank you.
Thank you, Maxence. Are there any questions for Maxence? Yeah, Anton, I think you raised your hand.
Okay, yeah, I have a short question. If you just go back one slide. So this, I haven't quite understood this G cross P over P. What does it really mean? Is it just G, or what's this product?
P acts on G by right multiplications.
Yes.
And on P by conjugation.
Oh, it acts by conjugation. Okay, thanks.
Okay. Chen, you're raising your hand. Please go ahead. Oh, you're muted.
Yeah, switch on the. Yeah, thank you for your very nice talk. Thank you. I just have probably just curious about, like, in which sense this is the TQFT. This more I forgot the name. Let me have a look.
The Moore-Tachikawa conjecture.
Yeah, a Moore-Tachikawa. In which sense is a TQFT? Because usually for TQFT, you sort of I guess it's 2D. I mean, I'm also not so good, but somehow you assume yourself, you go from the cobordism category, or then you end up with some category of vector spaces, right? So this quantized, but now you now it's only on these Lagrangians or Hamiltonians. Then you said that it's not yet Q yet. You need to do some GIT quotient. Is that the missing step? You get some vector space like stuff?
No, so well, a TQFT, as you said, is a functor from the category of cobordisms to category of vector space. That's the original definition of a TQFT, but we can define TQFTs to be other symmetric monoidal functor, just like define a TQFT to be a symmetric monoidal functor from cobordisms to any other symmetric monoidal category. And in this case, it's not the category of vector spaces, it's a category of Hamiltonian spaces where objects are Lie groups and morphisms are Hamiltonian spaces with these Lie group actions, and then composition is Hamiltonian reduction. So it doesn't have anything to do with the category.
I see. In this sense, it's just you change to another category. Okay, yeah, but still, you still need to do a GIT quotient to get
Yes.
another Hamiltonian space. You mean this?
Yeah, well, we don't have to do GIT quotients to get Hamiltonian spaces. The only issue is that if you do this only the normal quotients, what you get are just open sets of what you want. So for instance, the cylinder is supposed to be mapped to the identity, which is the cotangent bundle.
Yes.
But if you don't do GIT quotients, you'll end up with open subset of the cotangent bundle, like the set of regular covectors instead of the actual cotangent bundle. So you need to kind of take affinizations of these things to get the actual correspondences. And then that's why you take GIT quotients.
Thank
Does
you.
that make sense?
Yes, thank you very much.
Right.
Okay, Eckert?
Yeah, I have two questions. Maybe you said this, but I was just going a bit fast with this multiplicative Moore-Tachikawa.
Yeah.
Do you understand what happens for SL2C?
No, we haven't really tried to understand any specific example yet, but yeah, I mentioned SL3C would be maybe the conjugacy class, the unipotent conjugacy class for, I'm not sure what would be the generalization of, like in the additive case, it's the standard representation of SL2C, and you tensor it with itself 3 times. I don't know if you have an idea what would be the multiplicative version of that, but
I see.
That would be interesting.
Yeah, and the other question is, yeah, if I understand correctly, for these quasi-Hamiltonian spaces with group variant maps, we always had this problem that in general you cannot reduce with respect to a subgroup, and here you seem to have resolved this riddle a little bit, it seems.
Yes.
But the one special case that we could always do is if the group is G times G, and you reduce with respect to the diagonal. Yeah. Because then you could say you take first the fusion product and then you reduce. So does that fit into the story?
That's a good question. I haven't thought about directly recovering this fusion thing. Yeah, we'll think about that. That's a good comment. Maybe see. Oh, sorry.
Yeah, I can make a comment about that. So, we're also wondering about how to interpret the fusion product in this Dirac setting, and we don't really have an answer to that. But the quasi-Hamiltonian reduction of the fusion product at a point does appear in our paper, and we found some way to express it as a fiber product of Dirac realizations. Maxence, am I saying the right thing?
Yeah, exactly.
Would it be fusion product just composition of Lagrangians? So these Hamiltonian spaces are Lagrangians, some sort of maps, right? And I guess the fusion product of two such is just composition of these maps.
Yes. Yes, it would be this, but the question was about this construction of quasi-Poisson reduction by a subgroup. If we can view it also, I mean, if it can recover quasi-Poisson reduction while you have the fusion product, which it's a good question. We'll think about that.
Okay, are there any other questions for Maxence? Okay, so if there are no more questions, let's thank Maxence once again for a nice presentation.
Thank you.
Okay, and the next talk is in a fortnight, and it's by Gus Schrader. See everyone. Bye.
Bye.